Thank you, Morris, for the generous introduction. I see a lot of familiar and curious faces today. So thanks for stopping by for the talk today. So today we'll be talking a little bit on AI inferencing, starting off what is possible on the edge. Yes, you heard it right. AI inferencing can be done on the edge, not necessarily on the cloud. And then how do we transition that to a cloud within the reach and scale it provides. I also have my partner in crime, Akash. He'll actually show what I'm showing is not all academic. This actually, we have done a lot of commercial deployment, and Akash will walk through, a practical application that we have deployed, and then you can see some of the benefits of how inferencing on the edge actually helps. So with that, let's get started. When you look at the AI application development journey, I've been in this space for give or take about 20 years. And most of the applications or use cases kind of started in the perception space. Perceptions here meaning it's about detection, classification, segmentation, enhancements, all about audio, image, text, video. I know to a large extent it's still important today. You can see them widely deployed in IoT markets, AR glasses for sure. But from my perspective, it's mostly commoditized. You know exactly what needs to get done. It's all about speeds and feeds optimization. Give or take about 3 years ago, there was a lot of craze in the market wherein we had DALL-E and ChatGPT announced, and the world completely transformed on not believing in real data, but all about synthetic data creation. Qualcomm was one of the very first vendors to actually show that synthetic data can be created on the edge. You don't really necessarily have to rely on the cloud. And we were able to demo that at MWC. So I'll kind of walk you through that journey and what actually means on generative AI. And this year we have transitioned a little bit ahead by moving into an agentic space where it's all about, if I move towards an appless environment, my phone has about 150 apps, my PC has about 55 apps. I barely can even understand what it means. So I'm kind of using the voice as a primary interface and then trying to see if I can use that to really look at action generation and make it more repeatable, explainable, and a lot more accurate. So that's all about agentic flows and how we're trying to look at consumer and enterprise deployment. Last but not the least is all about physical AI. I'll not touch the physical AI portions today because it's a little bit in the research phase where it's all about how do you look at large, I would say, models like vision, language, action-based models. You interface that with perception models, and then can I get autonomy into humanoids? And I wish I could get a humanoid who could cook for me or wash the dishes at home, so I can be a good husband to my wife, right? So hopefully that scenario comes much more faster than later. Okay, so let's get started with with the generative space. A quick touch on the trends lines. At Qualcomm, we participate with a lot of model creators, a lot of model builders, a lot of OEM partners, Samsung, Meta, Google, GM, BMW. You name most of the tier 1 OEMs, we work with them quite a lot. And what are some of the trends that we have seen is most of these small language models, the SLMs, the quality of the SLMs are kind of improving quite nicely. And there's been a lot of emphasis on these small language models to no longer be very frontier or foundational, meaning not be jack of all trades, but a lot be more domain specific, task specific, so that they can have a lot more accuracy, less of hallucinations. So that trend is quite nicely increasing. And the size of the parameters of these small language models are very variant. You can see models which are coming in the 1 billion space, going as much as 50 to 70 billion parameters. And depending upon the swim lanes, we try to introduce different models, and I'll kind of walk you through where that actually happens. The second big trend is most of our partners are asking us to transition from instruction-based to reasoning-based models. Why is reasoning-based models is important? Is because you want these large models or reasoning models to think like a human, reason like a human. But it does not mean that if somebody asks a question, what's the capital of Portugal? You don't want these models to say, let me think for a while, right? That's not the intent. The question really becomes is, at what point do you really instantiate a reasoning model, and what point do you instantiate an instruction model? But you have to be prepared for both. So that's why we're trying to put a lot more focus on both these variants. The other important trend is also context length. Why is context length important? Because it is foundation for what we do towards personalization. And personalization is very critical for us because what we're seeing today in most of the AI inferencing use cases is very generic in nature. And at Qualcomm, we put a lot of emphasis to really make sure we transition from a generic inference to a personalized inference. Personalized inference is how do you make the response portfolio that matches the emotional intelligence of the user? Can I get the contextual information around you and then provide a response? If the response that you want to provide to a 6-year-old or a 60-year-old needs to be adaptive depending upon what the child or an old age person can understand. You don't want the response to be presented to a 6-year-old where the 6-year-old has to go look at an Oxford dictionary to really understand what kind of nomenclature is this large model actually spitting out. So these kind of things is all about personalization, and for that you need to know context, you need to know the emotional IQ of the user. So that's what we put a lot of emphasis. These are hard problems, and at Qualcomm we love working with these hard problems and then try to productize it on the edge. So again, a quick preview of the trends, because this lays the foundation for what we are trying to do moving forward. Now, you might always ask the question, why edge? Cloud is always easy. And I would not disagree with you. No, cloud definitely provides the reach and scale. It's quite popular today. But when you want to look at user privacy, when you want to look at personalization, when you want to look at responsiveness, edge becomes extremely critical, right? So that's what we've been trying to focus on the left-hand side. But I'll be the very first one to admit is inferencing on the edge is not easy. It is hard, and it's damn hard. But we've been doing this for the last 20 years. So it is, so we kind of know what are some of the secret handshake, what needs to get done from an infrastructure standpoint, so developers like yourself can actually scale on the edge with a lot more ease. Some of the challenges is, when you work on plethora of edge-based platforms, an IoT platform, AR, XR, VR, glasses, automotive, phones or PCs, the physical memory footprint is very different. And because of which, it puts an impact on what kind of large models can be stored on the device on the edge. Second thing is you always have limited bandwidth. Why bandwidth is important? Because it translates into token generation. Why is token generation important? Because it gives you better UX and better end-to-end latency. Smaller token rate or lower token rate, the response is very slow, the user is not engaged, and the human-machine interface completely collapses. So we have a challenge out there. And most of the use cases that our partners are looking for is also transitioning from on-demand to be more ubiquitous. Ubiquitous meaning it's running in the background at all times. It is not that you press an app, then the app comes up, and then you open up the model. When you try to make it ubiquitous, running in the background, energy consumption is paramount, is extremely critical. So it's very important that the amount of impact it has to the battery life is as small as possible. So again, few challenges. And I'll kind of walk you through, what are some of the foundational investments we are doing at Qualcomm, and how is it setting the way for the next wave of experiences moving towards the consumer and the enterprise markets. First one, what are some of the foundational investments? I'll touch on a few of them. The first one is all about quantization and compression. Why is this critical? When you look at large models, if you take the popular 7 billion model, either from Gemma family or from the Llama family. A 7 billion parameter model is almost equivalent to, give or take, about 13 to 14 gig of a memory space. That's huge. When you look at most of the phones, your phones are between 12 to 16 gigabytes. Your glasses are between 4 to 6 gigabytes. Your PCs are minimum 16 gigabytes going to 32 gigabytes. Your automotive environment is about 32 gigabytes. So if you want to play in the small form factor range and you want to have a 7 billion model and occupies 14 gigabytes, you absolutely have very little space, right? So it puts a lot of stress. And how do you look at quantizing it, and how do you compress the model so that the physical space or the memory footprint occupied by the model is as small as possible? So it's a difficult problem, but we have a ton of engineers who put a lot of emphasis on that to really look at making sure we're able to compress that model. And the most important thing, don't impact accuracy. If you impact accuracy, then it's no point compressing the model. Second one is all about improving a token rate. As I mentioned, most of the edge-based platforms, you don't have access to high bandwidth memory. HBMs are quite premium. They're mostly on the servers or on the edge appliance space. We work with a lot of LPDDR, which is low bandwidth DDR, coming from multiple memory vendors. And if you look at DDR4, DDR5, DDR6, best case scenario, we're about 100 to 120 gigabits per second. So by definition, At best, you can get between 20 to 30 tokens per second for a 7 billion model, which is okay, but not the best. Most of our customers are asking for pushing the token rate to be equivalent to 100 tokens per second, if not higher. And that's almost impossible to really go with the bandwidth constraints. So what do? You have to look at elements of speculation. Speculation is, when you happen to have at a very highest level, a student-teacher model, you have a very small model, who was able to produce tokens faster, and then you have the teacher model, the model that the student tokens generated is always referenced by the teacher. If the teacher approves it, they say, okay, fine, go ahead and produce it. So we kind of able to do that, and I'll give you an example how we're able to accomplish it, and that pushes the token rate to about 3 to 4x than what you would see with the traditional LPDDR challenges. Next one is all about distillation. Distillation is extremely critical, especially when you want to look at content creations. Content creation models today, you could look at stable diffusion models, you could look at Sora models, all about video and image. They're quite big. Now the question becomes, are they able to host those big models on the edge? As I mentioned, the memory footprint is quite large. So what we look at is distillation, wherein you take an open source or a smaller model, you train the smaller model to behave or mimic like these bigger models and able to deploy it. Now you're not able to get the exact accuracy that where these large models are able to get it done, but to a large extent you're able to really mimic what the user is looking for content creation use cases. And if that content is not to the best of satisfaction of the user, then you move towards a larger model that's hosted on the cloud. And last, a few other elements is all about personalization and efficiency, which is all about hardware, what kind of optimizations we do on the hardware side to really make sure that the energy efficiency is important. We don't go into gigawatts or megawatts of infrastructure. Here it's about can I get most of these inferences completed in single digit or double digit milliamps, because that's the metric, and it's extremely hard problem when you want to really look at token generation at that low power wattage. Okay, for today's talk, all this we could take a day to talk. I'll talk on the first two topics. Hopefully it kind of gives you a preview on what we have been doing on the Qualcomm side, and hopefully excites you on how we could how Qualcomm is actually pushing for innovation on the edge. The first one is on quantization and compression. I'll take the 5 Silica LLM model. It's a 3.8 billion model. We had an opportunity to work with the Microsoft Advanced Sciences Group, very good partners with us. On the left-hand side, here you can see the allocated space for us was 7 gigabyte. In other words, the 3.8 billion parameter model, if I take an FP16 representation, gives you about 7.7 gigabytes. We were able to quantize it to approximately 4 bits, and you're able to get to about 2.5 gigabytes. So that's roughly less than 50% of what you would accomplish with an FP16 model, which is okay. Now it's not that impossible, but we wanted to be a little bit more ambitious to say, guys, can I squeeze and get the memory footprint to be a lot more smaller? We transitioned towards 2 bits. Now 2 bits, when you want to go from 16 bits to 2 bits, is quite challenging. But obviously, we have a lot of pipelines. We looked at accuracy, optimizations, and we were able to get it down to approximately 1.2 gigabytes. This is very critical for us, a major accomplishment working closely with Microsoft. Why this is important is because now we're able to launch a 14 billion reasoning models on the edge-based devices, in this case a Copilot plus PC on XLE platforms. Again, I'm not making up, it's a 14 billion parameter model running on the edge. And this is not instruction-based, it's a reasoning-based models. And this lays the foundation for some exciting use cases, what we could do towards agentic flows. And the memory footprint for this is approximately 7.8 gigabytes. If I want to host the 14 billion parameter model in its native 16-bit format, that is close to 28 gigabytes of memory, which is almost impossible on most of the edge-based platforms. So this is something which is what we are looking for, and we're trying to push for it. So that's already commercial. We're going to see this in most of the Snapdragon X Elite-based platforms quite soon, and we're going to percolate that onto other form factors as well. Next one, let's touch on token generation. As I mentioned before, I'm using a 7 billion model. The prompt that we're using is recite the first law of robotics. If I use the default flow, this is how it would look like, give or take, right? About 15, 20 tokens per second on a 4-channel LPDDR-based family gives you, good response. The response is a robot may not, injure a human being, which is fine. It's slow. It gives you the right response. You're happy with it. But most of the use cases are kind of not in that space. As I mentioned before, most of our ecosystem partners are pushing us to go towards 100 tokens per second. Why is this important? Because as you move towards an agentic flow, what you're going to see is one LLM is triggering a different LLM is triggering a different LLM. So speed is the mode. So it's very critical that you're able to generate higher tokens to be in a position to have series of operations that these multiple LLMs are able to instantiate simultaneously. So here we have the teacher model on the bottom side, the student model on the top side, what we call as a draft model. Same question, and see how you're able to get it done. And in this case, as I mentioned, the rough speed is approximately 3x that you would see on a traditional non-speculation based model. And we've also deployed this into production. Same model, ask a question, how can I solve a Rubik cube? You can see the quotation that is able to provide with a very clean response in a matter of seconds. This actually is quite liked by a lot of our developer communities that we work with, a lot of our OEM partners that we work with, and we're trying to see if we can continue to push this to other swim lanes, other form factors, so a lot of these interesting use cases can be established. Okay, so now moving away from the infrastructure side, now most of the use cases I mentioned, again using the 2 examples of quantization, compression, speculation, how does it really help? It does to support a lot of monolithic use cases, especially in the productivity space and in content creation space. And this is spread across all swim lanes of Qualcomm form factors, either be IoT or XR or automotive. You see a lot of this already deployed, a lot of external pull, and a lot of use cases actually leverage this infrastructural advantage. But now let's move on to a slightly different scenario of use cases. What we're seeing from a lot of our partners is now we're transitioning into compound systems. What is a compound system? I've given you 4 examples on the left-hand side. I'll kind of walk you through one example. If you're asking us, an agent to say, please book a vacation for my family next summer, it's a very clear instruction. It's unfortunately very abstract in nature. The agent does not actually know when is the next summer, right? Summer could mean April, May, June, July, whatever it is, right? It needs to know exactly the month. It needs to have access to my preferences. Do I like to have a warm place to go as a vacation or a cold place as a vacation? It needs to know my preference. It needs to know the preferences of my family. When are my kids' summer vacation coming up? Does it overlap or doesn't overlap? And if I'm trying to do a booking, what kind of a preferred airline does it have to choose? What kind of routes do I choose? What kind of hotel preferences I would like? Do I like an aisle seat? Do I like a window seat? Do I look for a vegetarian option or non-vegetarian option? Again, they are a set of tasks that quite large in nature as part of one compound instruction. And that is very difficult to accomplish today with most of what you call single large language models. So we have identified this problem, and now we're trying to work with a lot of model builders, a lot of model creators, a lot of our partners to be in a position to solve that kind of problem. Right now, how do we do that? I've kind of given you a flow on how we at Qualcomm are focusing on agentic flows. Now, as part of agentic flows at the highest levels, we have, like I would say, 2 steps. The very first step is able to understand the intent of the user. The intent of the user is, hey, what is the user asking for? Is it a question in the navigation space, vacation, etc.? Or is it more in the financial space, more about paying a bill? Or more in the content creation space or content consumption space? Hey, I want to watch my favorite video in Netflix. kind of stuff, right? So you need to specify that into what specific domain does action need to get done. Once that is completed, then you have a certain set of tasks as part of that domain. The tasks, based on the previous example as mentioned, is trying to get the right booking, the airline, the food preferences, the hotels, all kind of stuff. And those are a series of models that does for each task. And those, when you kind of put them together, by definition, you're going to have, a series of, triggered action, which needs to be explainable, it needs to be accurate, and it needs to be repeatable. And those, I would say, at the highest levels, are the foundation for the agentic flows. Now, what I did not mention is you also need to create a knowledge graph about the user. The knowledge graph of a user is all about understanding, as I mentioned before, the emotional intelligence. What are some of your preferences? What are some of your choices? What do you like? What you don't like? And that usually comes by either your browsing history, what we call a screen understanding, based off your email compositions, based off your chat messages, all kind of stuff that you actually use your personal device for. And then you create a knowledge graph. This knowledge graph, obviously resides within the device. It's highly secure in nature. And it's only shared on the authorization of the user to the application that wants to use it. This is one such example that we're trying to push, again, asking a simple compound question, and how do you translate that compound question into a lot of experiences that the user expects it's repeatable, explainable, and accurate. Now, as I mentioned before, creating a knowledge graph is not easy. You need to be constantly, updating that knowledge graph based on, the user's history. But that's only limited to a single device. The knowledge graph, or the accuracy that you get from a knowledge graph, only improves if you're able to build that knowledge graph by constructing information for multiple devices. And that's what we at Qualcomm are investing significantly in, what we call as distributed on-device inferencing, which means if I happen to have a cell phone, if I happen to have a PC, if I happen to have a glass, and I drive a car, based off what the user is doing in those environments, can I share them? Can I get them concatenated? And that helps to really make sure I can augment the prompt with necessary pieces of information, so that these token generation or inferences is a lot more personalized for that specific user. This is one such example where we're actually going and putting this into production using glasses, a phone, and a watch, wherein you're able to understand a lot of elements around you, and then create these knowledge graph. And these knowledge graph always help these large models to be driving towards more user-defined agentic flows. Now, last but not the least, is, as I always mention, we do our best to drive towards personalization on the edge. But there's always going to be instances wherein the edge is just not been in a position to support or help out a user. There's always going to be instances wherein you happen to have a conversation with an agent on device. The agent on device says, I'm sorry, I just cannot help answer your question. At that point of time, it needs to go outside the device. It could be an edge cloud, which is on-prem, or it could be a central cloud, which is quite far away. But when this transition happens, it needs to have the contextual information that is shared between that stuff. And that's what lays the foundation of hybrid AI. Now, hybrid AI is not easy. Why do I say that? Because the routers that define the hybrid AI flows needs to be dynamic in nature. It needs to understand at what point do I make that switch from the device to the cloud. It is not predefined. Most of the hybrid flows today are predefined. In other words, if I ask a question about astrology, right, or if I ask a question on who's going to win the soccer World Cup 2 years from now, or the next one, those are philosophical questions, and by definition goes to the cloud. But these are things which are predefined, right? What we are trying to look at is, can I make these routers quite dynamic, and that's the most challenging part. Now, at the same time, also want to make sure that we put a lot of respect to our ecosystem partnership, because most of the talk which I mentioned before was all about what we're doing in the space of infrastructure, why we're investing in certain infrastructure trends to really push and make deployment a lot more easier. But at Qualcomm, we put a lot of emphasis working with our partners, and one such partner is Nexa AI. And Nexa AI provides a lot of support to developers to actually bring the state-of-the-art large models, with the day zero support on Qualcomm silicon. And these guys are largely focused on large models. Large models either be vision or language or text, whatever you can think of. And they're able to get it fully available across multiple backends, either be general purpose compute machines like CPU and graphics, and also could be a domain specific engine like the Hexagon NPU. In our case, if you're looking for better, I would say, time to first token, we usually ask our developer community to run it on the Hexagon NPU. But if you're looking at purely token generation, CPU, GPU, and NPU is totally fine. If you're looking at better energy efficiency, we push it towards the Hexagon NPU. Again, depending on what problem statement, what kind of KPIs you're looking for, we position one over the other. And our partner Nexa AI kind of gives you that guidance as well. And at the same time, they also work with a lot of model creators, either be from Alibaba, from Quen, from Microsoft, or from Google or IBM, to get you that day zero support. So you do not have to go through the problem statement of quantizing it, doing all the speculation to generate these binary models for execution on device. Nexa was able to do that all on day zero. At the same time, they've also created a playground called Hyperlink. I highly encourage you guys to play with the stuff. It's available for download. Currently, it's running on PC subsystems. And this Hyperlink as a playground is mapped to multiple models. And if anybody really wants to go check out, hey, what are some of the performance numbers? Am I getting what I'm looking for before I start developing any kind of applications mapped to those models? You could do that starting with Hyperlink. And as I mentioned before, you can, this is actually a multimodal model, and we highly encourage people to use our Hexagon NPU with the primary purpose, as I mentioned. We are really pushing for higher or better, I should say, token per joule, better time to first token, and higher token rate. If you're looking for higher token per joule or for better time to first token, definitely move towards Hexagon NPU. And they make it available as Nexa SDK. It, as I mentioned, supports the multiple backends. You also have the GGML format, which is quite popular in the developer community. That is totally available on our CPU, and you can use our OpenCL kernels, again, of choice to run it on the GPU. Again, multiple options depending on what you're looking for. The backend support is fully doable. Okay, with that, I'll transition to another partner of ours, bring in Akash, again showcasing some real examples of how the infrastructure we have developed, what kind of interesting use cases runs on device. With that, Akash, all yours.
Hi, my name is Akash, and I'm the co-founder at Whispp. We develop speech technology for people with voice disorders to help them communicate. Sometime back, a throat cancer patient reached out to us. After his surgery, he lost his voice. And without vocal cords, he produces whispery sounds, and he has this raspy voice. Immediately, we got to work. We took a bunch of his audio samples from before his surgery, and we created a personal voice. So now when he uses Whispp to talk with his wife, he hears his own voice. I'm going to play a short video of this person and his wife. He's going to listen to his personal voice for the first time. The video is in Dutch, so I hope you're able to look at the subtitles. It's a really powerful moment to hear your voice once you've lost it. And Ruud is not alone. Worldwide, there are 300 million people with some sort of voice disorder. They lost their voice because of a disease or they stutter. The core problem is such people, they cannot say what they want when they want to. And this is where we come in. We enable such people to communicate in real time via phone call, video call, or in a group setting that they are able to just carry their phone and have a conversation with people. We started off as an assistive technology, but over time, we've evolved into a far more enabling technology. You might recognize that you are in situations where you need to take a private call or a confidential phone call. Now you can use Whispp by steering your voice into a whisper, and on the other side, people still hear your own voice. Also, if you're in a very highly noisy situation, such as a construction site, you can still use your own voice. And this is made possible by our foundational audio-to-audio model, which is language agnostic, which means that you can speak any language, you can change languages mid-sentence, and Whispp converts it into your own voice in real time, less than 100 milliseconds, and we run on the edge. We develop mobile and desktop SDKs. So on the mobile, you are able to make phone calls and video calls. On the desktop app, we integrate with every communication platform there is, Google Meet, Microsoft Teams, etc. So people can have a voice video call. So in the last year, we've tried to move from our cloud AI to on-device AI. So we started off by making the models really small to put them on device on the CPU. Some of the constraints here is, in a real conversation flow, the model inference has to be really fast. We work on small audio chunks, like 40 milliseconds or so. So every second, we perform inference 20 to 30 times. And a video call can range anywhere between a few minutes to sometimes a few hours. So it should have a good sustained usage. But what we found was on the CPU, you have really unstable inference times. So depending on what background apps are running, it can change the entire experience. The device can get really hot, and the power consumption is high. So we wanted to immediately check out is how can we leverage Snapdragon NPU to run this model so we can run it on both laptop and on the phone. And we had to perform a few steps to make this ready. First of all, we had to prepare the model for the NPU. We had to develop a package around the NPU for the NPU so we can run it. And finally, we wanted to monitor how the NPU performs. We built our model from scratch, and it has a lot of custom operators. And to get it running on the NPU, we took a really practical approach, which is take our model, put it onto NPU, make an inference. If it gives you some errors, find out what are the problematic operators, replace them, load them on the NPU, and rinse and repeat. So this led us to a model which was completely compatible on the NPU, and we trained it. Once you've trained the model, we wanted to optimize it specifically to run on the NPU. And here, you can go, there are multiple ways of doing it, and both PyTorch and ONNX give you tools to do this. But I want to highlight the tools from Qualcomm because, especially on the Qualcomm AI Hub, all you need to do is upload a model and you select the target. In our case, it was the Snapdragon X Elite chipset, and you get an optimized model. There are multiple ways of doing this optimizations. Again, it's out of the scope of this talk, but I highly recommend you to try this out. Once you have the optimized model, we created a C++ package, wrapped the model around it, and essentially the C++ package calls the Qualcomm SDK, so it is able to run on both smartphone and on the laptop. On the smartphone, we used LiteRT or TensorFlow Lite because it was the recommended approach, and we used ONNX on Windows. Here another tool, another way to go about it is to compile your models into the Qualcomm's QNN framework because this is highly efficient, and it also avoids on-the-fly conversion. So when you load the model, it's instant. This also provides a really good user experience. Finally, how do you measure this? So we trained the model, we optimized it, we are able to load it onto NPU. How do you monitor its usage? Here again, you can do, Qualcomm provides you a lot of profiling tools that you can use to exactly find out which are the hotspots in your model. We took a practical approach again here to find what's the inference, what's the time per inference cycle, because for us, sustained usage is important. This is a screen recording of our desktop application and our desktop application running. So what we built is a virtual microphone. Consistently, it keeps getting audio from the hardware microphone. It processes it, and it sends it to the different communication platforms. So on the left-hand side, you see the inference in milliseconds, and you see the NPU usage currently is 0. That's because this is a CPU model. What you can notice is that the inference time per cycle highly varies. It can be 50 milliseconds, but it can also be up to 200 milliseconds. And this is when the laptop was plugged into power. And this is problematic for us. So what we did is we ran the same model we loaded the same model on NPU. And what you notice is it performs at about 40 milliseconds. And specifically in this case, we also loaded we used the setting of battery efficiency on the laptop, and we did not actually see any difference in the performance of the performance on the NPU. To wrap up, the NPU, we had a lot of advantages for moving from CPU to NPU. Your inference times improved, but it was also very stable. So we ran it for multiple hours, and we get the same inference, same performance. The device is relatively cool compared to when you use a CPU, and it's very efficient in power consumption. And one of the big advantages of using NPU is also it opens up the possibility to increase your model size, thereby improving the expressivity and also quality. Thank you.